This is the video project task 3 for Peter Samouris, s3722199. In this project I was tasked with selecting an indeterminate structure and analysing it. Last year I had completed an analysis on my veranda in structural analysis, so I chose to analyse the same structure in this course but was given a revised loading scenario. A uniformly distributed load is placed along the top beam and column of my veranda, with its magnitude dependent on my student number to create variability amongst my classmates. To make this structure determinate, I changed the support conditions from pin and roller to pin and pin to give me a degree of indeterminacy of 1. The purpose of this project is to apply different analysis methods of forces within a structure and investigate whether they yield similar results for the same loading scenario. Since loading remains unchanged in all scenarios, it is expected that the forces found with varying methods would produce similar results. The first method used was the force method of analysis, and it is founded on the premise of removing one of the support reactions, solving for it using integration, and then reintroducing that removed force into the final structure, making it determinate. From this point, we recalculate all the reaction forces and solve for the bending moments within the structure as we would normally for a determinate problem. Also take notice how the reaction forces vary slightly when Cx is reintroduced into my structure. Following the force method, students were tasked to analyse the same structure using the slope deflection method. To begin, we find the fixed end moments of the beam and column, develop equations in terms of EI and theta using a general formula, where theta is the slope at the denoted joint. Once solving for each of the angles, we can then solve for their bending moments. Once found, we can use simply supported beams to solve for the shear force at each joint, enabling us to plot the shear force distribution. The moment distribution method takes a different approach. Unlike the other two methods, the first steps require us to calculate the member stiffness factors, K, which take the moment of inertia, I, into consideration over the length of the beam. Once determining these, I calculated the distribution factors, then using the same fixed end moments that were utilized in the slope deflection method, I began my analysis. Seen in the table, we combine the FEMs about joint B, release the moment by changing the sign, apply ratios, and carry over the moments to each respective joint, all the while reducing them 50% each time. Pin ends do not pass back any moment, hence why we see 0 on the left and right hand sides. We continue iterations until values are within 0.5 kilonewton meters, then sum them up and plot the distribution of the moment. In a similar manner to the force method, I was then able to calculate the shear forces at each joint, leading to the plotting of the shear force diagram. Due to this method considering the different dimensions of the beam and column, we can notice that the moment values reflected. The column's moment of inertia is approximately 60% larger than that of the primary beam, and as a direct consequence, the moment in the column about joint B is also reduced by about the same 60%. The final method, approximate analysis, requires us to assume the locations of 0 moment by ratio of the span, and then place hinges at these locations. In order to assist with this, I back-referenced my force method and computed the point of 0 moment occurred at 0.2 times the length of the beam, while in the column it was more centralized at 0.4 times the length. This method takes a more simplistic approach, where I take into consideration 2 load cases, the top or the side load individually. Then in each case, we analyze each the beam or column on the left or right or the top and bottom sides of the hinge. In these computations, we first calculate the reaction forces and then solve for the internal forces, allowing us to calculate moments. In summary, each of the four methods used to analyze indeterminate structures all provide similar results. Variability is introduced in the moment distribution method as I is not held constant anymore, leading to a slight variation in the results of the moment about joint B. In saying that, the shear force diagrams are nearly identical in each method, proving how these methods are all viable ways to calculate forces within a structure, leaving it up to students to choose the way they prefer most going forward into the workforce. Thank you for listening.